talking about black holes. In particular, it is actually, hello? I might have to hold it. Yeah, so I'm going to be talking about supermassive black holes in particular and the connections that they have to the galaxies they reside in. So I'm going to spend most of the time focusing in on the black holes and a sample of unusual nearby galaxies. And then at the end, I'll spend some time describing a new large observing program I'm leading using the 8-meter Gemini North Telescope that's aimed at trying to address the biases and the kinds of galaxies for which black hole masses have been measured. And so hopefully along the way, I can convince you guys that this is an exciting field with a lot left to be learned. Okay, so let me just start with a reminder of what happened about 100 years ago. Shortly after Einstein published his theory of general relativity, Paul Schwarzschild solved Einstein's field equations for a non-rotating spherical body. This solution describes a black hole where the gravitational field is so strong that nothing, not even light, can escape. So an important aspect of a black hole is its event horizon, which is the point of no return. Basically, the event horizon is what makes the black hole black. The event horizon is located at the Schwarzschild radius, which depends on the mass of the black hole. So this means anything can become a black hole if you can figure out how to compress it down to the size of the Schwarzschild radius. So while physicists have been trying to understand the theory behind black holes, astronomers have been out searching for real-life examples of black holes in the universe. One of the first discoveries of a black hole, although it wasn't initially identified as that, came about 50 years ago by Martin Schmidt. Schmidt examined 3C273 and found that even though this object looked very much like a star, it was point-like and compact and very bright, it was actually quite far away from us. So it's at a distance of 750 megaparsecs, or 2.4 billion light years. So a parsec corresponds to about a light year. So over here I'm showing just a modern day image of 3C273 taken with the Hubble Space Telescope. So as you can see, there's a lot of light coming from a small region. If you carefully subtract off this point source, you're left with this fuzzy blob. And that's actually the underlying galaxy. So 3C273 belongs to a class of objects we call quasars. And these things are so bright that they actually outshine the galaxies they reside in. We now know that this tremendous amount of light we're seeing is due to the accretion of material onto a very massive black hole. In this case, the black hole mass is 9 times 10 to the 8 solar masses. So as material is falling onto the black hole, it reaches high speeds and it heats up to very high temperatures of over 1 million degrees. And so therefore it becomes very luminous. Around the same time, X-ray binaries were also being discovered, which we now know is also another phenomenon that requires the presence of a compact object like a black hole. So Cygnus X1 is a famous example, and it was discovered the first time around 1964. So this is a very bright X-ray source located in our own galaxy, and it turns out that this is an object that's a 15 solar mass black hole that's being orbited by a companion star. So material from the companion star is being accreted onto the black hole, and just like with the previous example, it's the accretion onto the black hole that's producing the very energetic and powerful X-rays. So some of you might know that Cygnus X1 was actually the subject of a famous bet between Kip Thorne and Stephen Hawking, where Stephen Hawking was betting that this object was not a black hole. He finally conceded that he was wrong in 1990 due to the overwhelming observational evidence, though. So as you can see with these examples between Cygnus X1 and 3C273, black holes come in a wide range of masses. So black holes can be as small as a few times the mass of the sun. These are called stellar mass black holes, and they're formed when massive stars run out of their nuclear fuel. We think that stellar mass black holes reside in large numbers throughout galaxies. In contrast, supermassive black holes weigh 1 million to a few billion solar masses, and they reside at the centers of galaxies. Exactly how supermassive black holes form is still a mystery. It's still very much an active area of current research. One theoretical scenario is that the death of the first generation of stars, which we think were much more massive than the stars we see today, could have produced the first black holes with masses of about 100 solar masses. Through the accretion of material and the merging of galaxies, those first black holes could have grown into the supermassive black holes of today. Okay, so you might be wondering, what about this regime between stellar mass black holes and supermassive black holes, are there black holes out there that weigh, say, 1,000 times the mass of the sun? The answer is we think so, but with the current technology, it's really difficult to unambiguously confirm the existence of these intermediate mass black holes. So for now, there is the possibility that intermediate mass black holes exist in clusters of stars associated with the galaxy or in very small galaxies with masses less than the Milky Way. Studying intermediate mass black holes, though, is especially interesting because, as I just described, they're likely the building blocks of the larger supermassive black holes. So studying intermediate mass black holes can provide you with information about the formation of supermassive black holes. Now, I'm interested in the most massive black holes in the universe, and so for the whole rest of the talk, I'm only going to be focusing on supermassive black holes. So beyond searching for black holes through accretion signatures, you can also look for black holes through dynamical methods. The strongest case we have for the presence of a supermassive black hole, of course, comes to the center of our own galaxy, where we can track the paths of individual stars as they orbit very close to the black hole. So here I'm showing a view of the center of our galaxy. The Milky Way is about 30 kiloparsecs across, and the sun and our solar system reside in one of the Milky Way spiral arms, located about 8 kiloparsecs away from the center of the galaxy. So we sit in the plane of the galaxy in its disk, and so as we look toward the center of the galaxy, there's just a whole bunch of stuff in the way, like dust. So that's what you're seeing here in this optical image. So this is a movie that's actually going to zoom down into the center of our galaxy. At some point, it's going to switch over to near-infrared wavelengths, which is better at seeing past all of this dust. Eventually, you're going to see a grouping of stars, and then we're actually going to zoom down even further and focus in on an animation of just a few stars orbiting around the black hole at the center of our galaxy. So this upcoming animation was based on actual data that was taken over the past 20 years. So each side of this box corresponds to 0.1 light years. So there are two stars that are especially important. One is SO2. It has an orbital period of 15.8 years, meaning that we've now seen one full orbit. And another important star is SO16 because it comes a mere 12 light hours away from the black hole. So from these observations of the stellar orbits, we can place very strong constraints on the enclosed mass, and that turns out to be 4 million solar masses. Furthermore, given how close some of these stars get to the center of the galaxy without being ripped apart or swallowed up, that places a maximum radius on the central dark object. If you remember from what I said before, a black hole forms when the mass can be confined to within a Schwarzschild radius. To be honest, these observations don't quite constrain the 4 million solar masses to within a Schwarzschild radius. We've yet to be able to get any observations right at the event horizon for any black hole. However, astronomers can't think of any other possible explanations. Only a black hole is dense enough to contain 4 million solar masses within this very small space we see. Now, beyond the Milky Way, black holes have been dynamically detected in about 90 galaxies to date. So dynamically searching for black holes requires observations that probe the very central region of the galaxies, where the gravitational potential from the black hole dominates over the rest of the galaxy. This region is called the black hole sphere of influence. So this is larger than the Schwarzschild radius, but its size is still pretty small. For a typical black hole, with a supermassive black hole with a mass of about 10 to the 8 solar masses, the black hole sphere of influence is roughly tens of parsecs. So resolving such small spatial scales with the current observational facilities really limits our measurement of black holes to those that are nearby, roughly within 100 megaparsecs. So the Hubble Space Telescope, with its superb angular resolution, has therefore played a fundamental role detecting black holes in galaxies. More recently, though, significant progress has been made using adaptive optics, or AO, on large ground-based telescopes. So AO corrects for distortions due to the Earth's constantly changing atmosphere. So without AO, on ground-based telescopes, stars appear blurry. So this is an example. It's an image of the galactic center taken with one of the 10-meter Keck telescopes without AO. When you turn the AO system on, the stars appear much more sharp, which you can see down here. So AO on large ground-based telescopes can provide similar angular resolutions as HST, but it has the added advantage of being used with larger telescopes. So we're talking about an 8 to 10 meter class telescope as opposed to a 2.4 meter telescope. Also, these AO systems operate in the near infrared. So all of this means that galaxies that were previously really tough to observe with HST because they were a little too faint or a little too dusty can be studied in great detail with AO on large telescopes. So from HST observations and AO-assisted large telescope observations, we've found that the masses of black holes correlate with the large-scale properties of the host galaxy it lives in. We find that more massive black holes are found in more massive galaxies, where roughly speaking, we expect the mass of the black hole to be about 0.1% of the host galaxy's bulge mass. So a galaxy's bulge is just this central concentration of stars. So for a galaxy like this one, the bulge is this like spherical light distribution at the center, whereas for a galaxy like this one, an elliptical galaxy, the entire galaxy is the bulge. I want to emphasize, though, that bulges extend very far away from the black hole. They're not directly influenced by the gravity of the black hole. So this means that it's really surprising to find that the masses of black holes correlate with galaxy bulge properties. So this connection between black holes and galaxies suggests that they somehow grow in tandem. So the very broad picture we have for how black holes and galaxies grow together is tied to galaxy mergers. When galaxies merge, material gets channeled toward the center, feeding the black hole and triggering its formation, thereby growing both the black hole mass and the galaxy's stellar mass. As the black hole is actively eating up material, it's very efficiently converting gravitational energy into radiation. But as the black hole continues to grow, it releases more and more energy into its surroundings, which can heat up the surrounding material and it gets expelled. So that will shut off star formation and further limit black hole growth. In other words, the black hole is an essential component of a galaxy. It essentially prevents itself and the galaxy from getting any larger. However, the details of that very rough picture are poorly understood. In fact, you actually don't even need the black hole to actively influence the host galaxy. So numerical experiments have shown that you can actually get a correlation between black hole mass and galaxy mass from an initially uncorrelated distribution just due to the inherent averaging associated with random galaxy mergers. It basically boils down to like a central limit theorem and a statistical convergence process. So over time, with enough mergers, basically the extreme values of the black hole mass to galaxy mass ratio get averaged out and you just tend toward an ensemble average. In this scenario, you would expect that the scatter should decrease as you move toward higher black hole and galaxy masses, since those are the objects that experience the most amount of merging. Now this is a very extreme example. I'm really just trying to make this main point that even with the past 2 decades of research on supermassive black holes, we still don't have a solid understanding of their exact role in galaxy evolution. So black hole masses and large-scale host galaxy properties, there's been a number of correlations that have been found. 2 of the more well-studied relations are between the black hole mass and the bulge luminosity, or ML, and then the black hole mass and stellar velocity dispersion, or M sigma. So the stellar velocity dispersion is a measure of the random motions of stars in a galaxy. So despite the growing number of black hole mass measurements, the local black hole mass census is highly incomplete. This is particularly true for low mass black holes, below about a few times 10 to the 7 solar masses, and for high mass black holes above about a few times 10 to the 9 solar masses. So this leaves major open questions regarding the distribution of black hole masses and galaxy properties. So with the present black hole mass measurements, things like the slope, the intrinsic scatter, and even the shape of the correlations for low and high mass black holes are not well established. In fact, the M sigma and the ML relations make very different predictions for the black holes in the most luminous and the highest dispersion galaxies, and it's not clear how to reconcile the difference. The scaling relations aren't as simple as once thought either, and there are hints that perhaps these correlations don't apply consistently to all kinds of galaxies. So in order to address these uncertainties and really get at what the physical mechanisms are that are driving these empirical correlations, we need more black hole mass measurements in carefully selected individual galaxies and then in large samples of galaxies. In particular, we need to better probe the extremes of the black hole mass scale, and we need to study a wider range of galaxies that have undergone different growth pathways. we also need to do a better job of trying to quantify the intrinsic scatter in these scaling relations. So with the rest of the talk, I'm going to be describing several black hole mass measurement projects that are aimed at taking these necessary steps. So with all of that in mind, we began the HET Massive Galaxy Survey. So this is a large survey where we observed over 1,000 galaxies with the Hobby Evaluating Telescope, or HET, at McDonald Observatory in West Texas. The survey lasted over the course of 3 years, and we targeted galaxies with different combinations of stellar masses, sizes, and velocity dispersions. So with the HET data, we're able to measure the motions of stars on larger spatial scales, since the HET doesn't have an AO system. But this allows us to identify potentially interesting galaxies that we can then follow up with higher angular resolution facilities that are just more expensive to get time on. So really, the survey allows us to make best use of high angular resolution facilities. So from the HET Massive Galaxy Survey, we've uncovered a sample of galaxies that are ideal for studying the upper end of the black hole mass-host galaxy relations. These galaxies have small sizes and luminosities for their large stellar velocity dispersions. So here I'm just showing plots of common galaxy properties, so the infrared luminosity, the stellar velocity dispersion, and the effective radius, which is a characteristic size of a galaxy. So the gray contours show the nearby galaxy population from the Sloan Digital Sky Survey. The green dots are the galaxies we observed as part of the HET Massive Galaxy Survey. And then the black crosses are galaxies with published black hole mass measurements. So the compact, high dispersion galaxies I'm going to be talking about live in these regions that are circled in red. More specifically, these galaxies have effective radii of 1 to 3 kiloparsecs, infrared luminosities of about 10 to the 11 solar luminosities, and stellar velocity dispersions above 250 kilometers per second. So these compact galaxies are interesting because they could host some of the most massive black holes out there just based on their large stellar velocity dispersions. However, these kind of galaxies look very different from the types of galaxies you would expect to host the largest black holes. So as an example, I'm showing some galaxies here in the Perseus cluster. NGC 1275 is the brightest galaxy in this cluster, and it's the kind of galaxy that you would expect to find at the upper end of the black hole mass-host galaxy relationship. So galaxies like this one are large ellipticals, typically with effective radii of like 10 kiloparsecs, and they're often these dispersion-supported galaxies that show little to no rotation. So in sharp contrast to that are these compact high-dispersion galaxies. So NGC 1277 is one of the galaxies we found through the HET survey. As you can see, galaxies like NGC 1277 are small, they're flattened, and it turns out that they're rapidly rotating. And such host galaxies haven't been widely explored when it comes to the black hole scaling relations. Instead, galaxies like NGC 1277 appear remarkably similar to galaxies at a higher redshift of about 2, corresponding to about 10 gig-years ago. These are sometimes referred to as red nuggets. And then finally, these compact galaxies are interesting because the black hole mass, as predicted from the M sigma and ML relationships, are in direct conflict, with the masses differing by order of magnitude. Okay, so we've been working to obtain all the necessary imaging and spectroscopic observations needed to carry out a detailed examination of these compact galaxies. This includes acquiring HST images. So here I'm just showing some examples of the infrared, near-infrared images we have. With the exception of one galaxy, all the other galaxies appear very regular, and they don't show any clear evidence of having a recent interaction with another galaxy. We also need some large-scale spectroscopy for our dynamical models in order to constrain the stellar mass-to-light ratio, which is the parameter we use to convert from the amount of light we see into a mass. We, of course, have the HET data that were taken along the galaxy major axis for all the compact galaxies in our sample. So up here are some examples of the stellar kinematics measured from this HET data. So this is the velocity, and this is the velocity dispersion, plotted as a function of the distance from the nucleus. So the HET data are certainly useful, but it would be even better to be able to measure the stellar kinematics as a function of 2D spatial location. So we've also gone out and acquired such data using what's called an integral field unit, or IFU, at one of the telescopes at the Colloquium Observatory in Spain. And so down here are some examples of those stellar kinematics. So they're plotted as a function of spatial location. So again, this is the velocity dispersion. These values are plotted using different colors given by the scale bar to the right, and then the minimum and maximum values are shown to the top of the maps. So all of these large-scale kinematics are showing us that these galaxies are rotating, and they show sharply peaked velocity dispersion profiles, which suggests the presence of massive central black holes. Really, though, if you want to obtain a secure black hole mass measurement, you need high angular resolution spectroscopy. And so that's the part that I've been focusing on. We've been working to obtain AO observations using the IFUs on the 8-meter Gemini and 10-meter Keck telescopes in Hawaii. So far, we have completed observations of 6 of the highest dispersion galaxies in our sample. So all of these observations were carried out in the near thread, and we're able to make measurements within the central about 1 arcsecond region, which corresponds to 330 to 530 parsecs for these galaxies that lie at distances between 70 and 110 megaparsecs. With the AO system, we should be able to resolve the black hole sphere of influence if the galaxies follow the M-sigma relation. So in the next few slides, I'm going to be focusing on the 3 galaxies that were observed with Gemini, since those are the measurements I've finished. I'm still working my way through the Keck data. And just to bring everything together here, we're going to be using the HST images to measure the galaxy's luminosity density, and then that's going to be combined with the AO and large-scale spectroscopy in order to constrain the enclosed mass during the models. Okay, so unlike the galactic center case, for external galaxies, we can't actually measure the motions of individual stars. What we can do, though, is measure the velocity distribution of stars along our line of sight. We characterize this distribution with the center, the velocity, the spread, the velocity dispersion, and then the asymmetric and symmetric deviations from our Gaussian, H3 and H4. So in other words, the skewness and kurtosis. So with the IFU data, we're able to measure this distribution as a function of spatial location. So down here are just some examples of the Gemini data we have for NGC 1277. So these are spectra at 2 different spatial locations, located at the nucleus and then about an arcsecond away. So with these strong absorption features, with their shapes, we're able to measure the stellar kinematics, and that's what's being shown over here. So again, these stellar kinematics are plotted as a function of spatial location. This is the velocity map, and it shows that the galaxy is rotating. So one side of the galaxy is redshifted, so the stars are moving away from us. The other side of the galaxy is blue shifted, so the stars are moving towards us. And they're doing so with really high speeds of up to 350 kilometers per second. So that is really fast. Over here is the map of the observed velocity dispersion. And we're seeing a very dramatic rise in the velocity dispersion as we move in toward the center, reaching values of 550 kilometers per second. So these are the other 2 compact galaxies observed with Gemini, NGC 1271 and Mark 1216. So again, with these galaxies, we're seeing that they're rotating, and they have these very sharply rising velocity dispersion profiles, reaching values of 400 and then about 430 kilometers per second. Okay, so we then construct orbit-based dynamical models of the galaxy. The main idea is that the galaxy's gravitational potential consists of contributions from the black hole, stars, and dark matter. The stellar potential is determined by using an HST image and assuming a viewing orientation and a stellar mass-to-light ratio, so again, to convert the light into a mass. We set up a representative orbital library, and we integrate orbits in that potential. We assign weights to the orbits, such that the superposition will reproduce the observed kinematics and the brightness from the HST image. And then we just repeat. We calculate a whole bunch of different models, varying the parameters of interest, like the black hole mass, and then the best model is taken to be the one that most closely matches the data in a chi-squared sense. So these kind of models are computationally intensive, and depending on some of the assumptions that are made, you could have a high-dimensional parameter space to explore. So for that reason, we use supercomputers for this part. Okay, so this top plot summarizes the modeling results for the most recent galaxy we finished analyzing, Mark 1216. So these are contours of chi-squared as a function of black hole mass and stellar mass-to-light ratio. At each gray point, a model was calculated, and then the best fit model is that red square. The red contours show the 1 sigma confidence level. So ultimately, we're finding a black hole mass of 4.9 times 10 to the 9 solar masses. Down here is just the comparison between the observed stellar kinematics and then our best fit model shown on the same scale below. As you can see, the model does reproduce the observed kinematics nicely. I do want to mention that this galaxy has been previously studied before using just the large-scale stellar kinematics and orbit-based dynamical models. So with the large-scale stellar kinematics, the angular resolution was very poor. There was no AO system. And so with such poor angular resolution, you're unable to actually constrain the black hole mass very well. So just an upper limit was found on the black hole mass of 10 to the 10 solar masses. So our superior AO observations are consistent with the lower resolution spectroscopy, both in terms of the black hole mass and the mass to light ratio. Okay, so these are the other two galaxies. So again, for both of these, we're finding very massive black holes in the range of 3 to 5 times 10 to the 9 solar masses. Yeah. 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 Yes. Yeah, so that's a good question. It's something that some people have claimed that stellar populations are changing in this particular galaxy. What you do need to be careful about a little bit is that, you know, when you broaden things out, there's a degeneracy between how broad the absorption lines are and how deep they are. So, I mean, I know it looks like that there, you know, people are still trying to figure out if there's a change in stellar population in this galaxy, but that's definitely something that needs to be looked into more for sure. Yes, the Gaussian dispersion, yeah. Sorry. Okay, so the one last point I wanted to make on this slide is that we also tested some of the inputs into our stellar dynamical models, so some of the assumptions we're making in order to try to get some kind of handle on the systematic effects in our black hole mass measurement. So we actually built that into our final error budget along with the statistical 1 sigma uncertainties, and so those are the uncertainties that are being quoted here. Okay, so it turns out that NGC 1271, NGC 1277, and Mark 1216 host some of the most massive black holes that have been dynamically detected to date, with masses of 3 to 5 times 10 to the 9 solar masses. So these galaxies are consistent with M sigma, but they're positive outliers from ML. Now, this is true even when conservatively using the galaxy's total luminosity as opposed to the smaller bulge luminosity. These galaxies are still clear outliers. To hopefully convince you that these galaxies cannot lie on the ML relation, I'm going to use NGC 1271 as an example. So this set of plots on the left are the data. This is the velocity of dispersion and the H4 values. This middle set of panels are showing our best fit model with a black hole mass of 3 times 10 to the 9 solar masses. And then all the way over here on the right is the model with a black hole mass of 4.7 times 10 to the 8 solar masses, which is the mass that you'd expect based on the ML relation, even when conservatively using the galaxy's total luminosity. So as you can see, our best fit model is able to reproduce that sharp rise in the velocity dispersion, as well as the slight peak in H4 at the center, whereas the model based on the lower black hole mass that's based on ML can't reproduce either of these features. Okay, so now just coming back to the compact galaxies and the black hole scaling relations, this behavior of being consistent with M sigma, but being a positive outlier from ML, is actually similar to the two other compact galaxies that in the literature that have dynamical black hole mass measurements. So these are NGC 4342 and NGC 1332. So, and these of course are shown by the blue asterisks here. So all of these galaxies look very similar. They all have small sizes, they're all flattened, it turns out they're all rotating. They have elevated velocity dispersions for their luminosities, and all of them have black holes that are just too massive for their host galaxy's luminosity. So yeah, it'll be really interesting to see where the other compact galaxies in our sample end up once we actually do have black hole mass measurements for them. So this naturally leads to the question of how such large black holes ended up in relatively modest galaxies. One possibility is that we simply don't have enough black hole mass measurements at the upper end of the black hole mass-host galaxy relationships. Neither the form of the correlations nor the intrinsic scatter of the correlations is well established in this high mass regime. Therefore, these compact galaxies could simply fall in the tails of a distribution between black hole masses and host galaxy properties that we have yet to fully flesh out. Another possibility is a really interesting one, I think. As I briefly mentioned before, these local compact galaxies appear very similar to the higher redshift 2 so-called red nuggets. The red nuggets are thought to grow in size and mildly in mass through a series of mergers to produce the more typical local early type or elliptical galaxies of today. So perhaps our local compact galaxies instead have experienced a different growth pathway, and they have not experienced the same set of mergers to build up the outskirts of their galaxies. So perhaps the local compact galaxies that we're studying are relics of the redshift 2 red nuggets and reflect a previous time when the local ML relation did not apply. Galaxies instead contained overmassive black holes, and the growth of host galaxies had yet to catch up. In other words, galaxies like NGC 1271, 1277, and Mark 1215 could suggest that black hole growth precedes that of its host galaxy. So before moving on, I want to point out that the Giant Magellan Telescope with its AO system will be outstanding for this kind of work in studying the upper end of the black hole mass-host galaxy relations. So it turns out that with GMT, the black hole sphere of influence for a 10 to the 10 solar mass black hole can be resolved throughout the universe, and for a 10 to the 9 solar mass black hole can be resolved out to a redshift of about 0.4. Now, of course, you still need to worry about getting the signal in order to do these dynamical black hole mass measurements. That's obviously a very important point. But for these high mass black holes, angular resolution is no longer a concern. This means that we can finally build up a statistically significant sample of high mass black holes by being able to search for them over larger distances. So with a large number of high mass black holes, we can finally more firmly pin down what the scatter and what the shape of the black hole scaling relations look like at this upper end. Furthermore, with GMT, we can begin to track how the black hole host galaxy relations evolve over time. So more directly getting at this question of whether black holes and galaxies truly grow in lockstep with one another over time, or if the growth of the black hole precedes that of the host galaxy, as the HET compact galaxies were suggesting, or if perhaps the opposite is true. The growth of the galaxy comes first and then the black hole catches up later. So since with the current observational facilities, we can only make dynamical black hole mass measurements for very nearby galaxies, we really can't fully get at this question of which comes first with the current technology. Okay, so up until now, I've been discussing the results of stellar dynamical models. One of the other main ways of measuring a black hole mass is to model the rotation of a circumnuclear ionized molecular gas disk. So the main assumption here is that the gas participates in circular rotation in a thin disk. The potential consists of contributions from the stars, again as measured from, say, an HST image and assuming a stellar mass-light ratio, plus the black hole. During the modeling, we take into account various instrumental effects, and then ultimately the goal here is to compute a model that simultaneously matches the observed velocity, dispersion, and brightness of the emission lines. So the stellar and gas dynamical modeling methods have their strengths and weaknesses. Stellar dynamical modeling is the most widely used method, since the motions of stars reflect the underlying gravitational potential. However, these extracting a secure black hole mass measurement from the observed stellar kinematics can just be challenging due to the complexity of the models, which unfortunately are computationally expensive to calculate. Also, the models can be subject to a number of systematic effects, such as mass degeneracies between the black hole, the stars, and dark matter, as well as assumptions that you're making about the intrinsic shape of the galaxy, like whether it's axisymmetric or triaxial. In contrast, gas dynamical modeling is conceptually simple. However, the motions of gas can be influenced by non-gravitational forces, and so this assumption of circular rotation must be verified. Furthermore, many of the observed nuclear gas disks show velocity dispersions in excess of what you would just expect from bulk rotational motion alone. The physical origin of this intrinsic velocity dispersion is not known, but it could be dynamically important. And if so, it should somehow be included in the models in order to prevent a biased black hole mass measurement. So clearly, both the stellar and gas dynamical black hole mass measurements suffer from several but different systematic effects. Therefore, it's really important to directly compare the two in order to answer questions like how much of the intrinsic scatter of the M sigma and ML relationships is just due to inconsistencies between the two methods, or is there a systematic difference in the masses derived using the two methods? So one such galaxy for which both stellar and gas dynamical black hole mass measurements have been carried out now is NGC 1332. As I mentioned before, NGC 1332 wasn't found through the AGT Massive Galaxy Survey, but it does closely resemble the compact galaxies I've been talking about. So this is a nearby galaxy, again with a small size and a flattened structure, and it has this elevated stellar velocity dispersion for its luminosity. So NGC 1332 was observed with AO on the Very Large Telescope, so that's an 8-meter European telescope. And so down here are the observed stellar kinematics. So just like with our compact galaxies, this galaxy is rotating. I know you can't really see it, with velocities of plus and minus 160 kilometers per second. And it shows that sharp rise in the velocity dispersion to values of 420 kilometers per second. So based on these stellar kinematics and dynamical models, another group, Whistley et al. In 2011, found a black hole mass of 1.45 times 10 to the 9 solar masses. So with this mass and the bulge luminosity that they find, NGC 1332 contains a moderately overmassive black hole relative to the ML relation, but it is consistent with M sigma. So the gas dynamical black hole mass measurement for NGC 1332 was carried out very recently using ALMA observations. So ALMA stands for the Atacama Large Millimeter Submillimeter Array. So this is a new facility that's located in Chile, and it's currently composed of 40 12-meter and 10 7-meter radio antennas that are all just working together. Oh. Oh, really? I didn't know that. All right. Yeah, so ALMA is this radio facility in Chile, and basically it's just, I think it's going to do some really interesting things for the field of supermassive black hole demographics. So ALMA just provides this huge step up in terms of angular resolution and sensitivity compared to the previous radio facilities. So this enables the kinematic mapping of molecular gas disks on subarc-second scales, and therefore the possibility of accurately determining black hole masses. So the cold and dense molecular gas that we'll be looking at, the expectation is that it will have a smaller turbulent velocity dispersion compared to the warmer ionized gas disks that have so far been the subject of nearly all the gas dynamical black hole mass measurements. So one of the main systematics associated with gas dynamical modeling could be much less of a concern with ALMA observations. So directly detecting molecular gas within the black hole sphere of influence has so far only been possible for very few select nearby galaxies. In fact, the first ever black hole mass measurement based on molecular gas was done just a few years ago using this radio facility Karma. And in that case, the black hole sphere of influence was just barely resolved, even though this galaxy lies really close to us at a distance of 16 megaparsecs. And in that case, the observation required tens of hours to complete. So the expectation is that ALMA can just blow this right out of the water. So I've been part of a collaboration that's been using ALMA in order to measure black hole masses in this way. And one of the galaxies we targeted with early science observations was NGC 1332. So for NGC 1332, we obtained ALMA observations at 0.3 arcsecond resolution. We didn't know what to expect for how strong the molecular gas would be on these very small scales. And so we employed like an efficient two-step strategy. So we started at this somewhat higher angular resolution that would just barely resolve the expected black hole sphere of influence in order to first test for the presence of CO at the nucleus. So CO is the molecular gas that we're studying here. And then it did turn out that we found a nicely rotating molecular gas disk. And through some dynamical models, we found a rough black hole mass of 6 times 10 to the 8 solar masses. However, with this kind of higher 0.3 arcsecond angular resolution, we weren't really able to place very strong constraints on the black hole mass. So now knowing what to expect for the molecular gas at the nucleus, we then went back the following year and obtained much higher angular resolution observations with ALMA at an incredible 0.04 arcsecond resolution. And so with this data set, we were really able to place strong constraints on the black hole mass. So ultimately, we're finding 6.64 times 10 to the 8 solar masses with about 10% uncertainties. So the molecular gas kinematics is very highly inconsistent with the stellar dynamical black hole mass measurement. So this ALMA gas dynamical black hole mass measurement is a factor of about 2 smaller than the previous stellar dynamical black hole mass measurement. And it actually pushes NGC 1332 in line with expectations from the ML relation. So, right, yes, absolutely, yeah. I mean you mean between the stars and the gas. I thought you meant between the two. So, yeah, so I mean, there are a couple of things that might need to be improved with the stellar dynamical black hole mass measurement. Kind of one of the big uncertainties, I don't know, there's probably no image here. So it looks very dusty. So you need an HST image in order to measure the stellar mass profile, and it's very dusty. So how do you get rid of that dust and get the true stellar mass profile? Here, because we're with these set of observations, we're probing very, very well within the black hole sphere of influence. The stellar mass profile is it enters into the errors a lot less. But it was a problem up here, for these higher resolutions. Okay, so there have actually been very few consistency checks between the main black hole mass measurement methods, and they're actually all shown here. Unfortunately, not all of these objects even provide a meaningful comparison between the two techniques. So unfortunately, in these 3 cases, it turns out that the gas is not really compatible with regular disk-like rotation, and so they're not suitable for this proper comparison between the stellar and gas dynamical methods. In the case of NGC 4258, the gas dynamical black hole mass measurement just has huge error bars, so you can't compare to the stellar dynamical black hole mass measurement really. In the case of NGC 3227 and NGC 4151, the very bright nuclei due to the accretion onto the black hole just really complicates both the stellar and gas dynamical analyses, leaving kind of just uncertain measurements. So really this leaves these 4 objects, SEN A, M87, NGC 3998, and of course NGC 1332. So the most recent stellar and gas dynamical black hole mass measurements for SEN A are found to be in agreement, whereas unfortunately for these 3 galaxies, the stellar dynamical black hole mass exceeds the gas dynamical determination by factors of 2 to 3. So clearly we need to do more cross-checks like this in order to get at whether these methods are really consistent with each other, what the subsequent effects are on the black hole scaling relations, and for us to actually be able to get at what the intrinsic scatter is in the black hole scaling relations. Okay, so it actually turns out that about half of the compact galaxies in our HET survey show very well-defined, regular-looking dust disks. So here are some examples of those dust disks in HST optical images. So such dust morphology strongly suggests the presence of cleanly rotating molecular gas. And so I was recently awarded ALMA observations for this year in order to study 3 of the HET compact galaxies. So we're going to just be using the same approach that we used for NGC 1332, where we're going for a little bit higher angular resolution that will just resolve the expected black hole sphere of influence. And then we will study the kinematic and spatial structure of the molecular gas disks, fit dynamical models to derive a gas dynamical black hole mass measurement, and then if we need to, we can go back in a future ALMA cycle in order to really pin down that black hole mass if the angular resolution is insufficient. So with the exception of NGC, so all of these, none of these have previously been targeted with any millimeter or sub-millimeter facility, and so we don't know what to expect for the molecular gas on those small scales, with the exception of NGC 1277. So this galaxy has been previously studied, although it was done at 1 arcsecond and 3 arcsecond resolution, and so in that case, they couldn't distinguish between a 5 times 10 to the 9 solar mass black hole or a 10 to the 10 solar mass black hole. So something we definitely want to think about doing in the future is try to do this with ALMA so we can really probe deep well within the black hole sphere of influence and break the degeneracy between the black hole mass and the stellar mass light ratio. Okay, so studying the compact high dispersion galaxies was one interesting thing that came out of the HET Massive Galaxy Survey. But this survey also provides us with this excellent starting point from which to design a large black hole mass measurement program. So we're really excited about carrying out such a large black hole program. So we recently were awarded 253 hours spread out over the next 3 years to measure black hole masses in 31 galaxies using Gemini and the AO system there. So we've assembled this great international team. So all the Gemini partner countries are here, some other ones. So the goal of this program is to obtain a more complete census of local black holes in a wide range of galaxies that have experienced diverse evolutionary histories. So I'm again showing in this plot the galaxy infrared luminosity and the size. So again, these gray contours are the nearby galaxy population from the Sloan Digital Sky Survey. This time, though, the green dots are galaxies with published dynamical black hole mass measurements. So as you can see, the galaxies with black hole mass measurements, they've been made in a biased set of galaxies. At a given luminosity, galaxies with smaller sizes relative to the nearby galaxy population have been preferentially targeted to date, since those are the objects that are easiest to observe and model. Possible future black hole mass measurements based on already existing AO data that's just in the public archives, those are shown by the black dots. That's not going to alleviate the problem either. It's really important, though, to properly sample this luminosity size parameter space, though. So as you can see over here, as you move in this direction, so this direction, a whole bunch of galaxy properties change, like the stellar velocity dispersions, the mass-to-light ratios, the gas content, the kinds of stars that are in these galaxies, the galaxy morphology. So just as a reference and contrast, your typical massive, luminous, slow-rotating galaxies live up here. So yeah, we just need to do a much better job of sampling this important parameter space if we want to actually get at what the distribution of black hole masses is with various galaxy properties, and trying to get at the role of what black holes the role black holes play in galaxy evolution. That's what I'm trying to say. Okay, so we basically just started with the HET survey galaxies and looked for those that we could observe with AO and stellar dynamical modeling methods. So we applied some basic cuts. For example, we required that the expected black hole sphere of influence be at least 0.1 arcseconds. So that will ensure that we will resolve the expected black hole sphere of influence if these galaxies follow M sigma or if they follow ML. We also made a cut on how bright the central regions of these galaxies needed to be, since we want to be able to get high-quality data in some reasonable amount of time with this instrument on Gemini. We also made a redshift cut, since there are specific absorption features that we're interested in measuring in the near-infrared. So basically, with the remaining galaxies, we just tried to fill in this luminosity size parameter space as much as possible. So here in red are the galaxies in our sample. So the red numbers correspond to these images. These are Sloan images that are shown on the same physical scale. The red crosses are also in our sample. There's just no image shown. So as you can see, our sample significantly improves coverage of this important parameter space without sampling the already well-populated region within that dotted oval. There is this remaining unsampled region over here, and that's because the galaxies that live there generally have very faint central brightnesses. And so that would just take a really long time to do with our instrument. So yeah, I mean, our sample spans a wide range of galaxy properties. So for example, the stellar velocity dispersions range from about 60 to 300 kilometers per second. A lot of our sample is dominated by spiral galaxies. So we will nearly double the number of black hole mass measurements that have been made in spiral galaxies so far. So this is a regime that largely hasn't been tackled with stellar dynamical modeling methods. So we conducted our first observations in September of 2016. So we obtained completed AO observations of 6 galaxies using 36 hours of our allocation. So they're shown in blue here and over here. So we've observed the largest, most luminous galaxy in our sample, as well as some lower luminosity galaxies at different effective radii. And so with this even smaller subsample, we are already doing a very good job of enhancing the diversity of black hole host galaxies. And given that, we could find some surprisingly low or high mass black holes. So in addition to collecting this Gemini data, we do also need large-scale spectroscopy. So we've been using the 2.7 meter telescope at Jonelle Observatory, as well as the HET to collect that large-scale data that we need. And we certainly will be applying for HST time to get uniform imaging for this sample. So these are just some examples of the Gemini data that we got in September for 2 of the galaxies. So these are spectra that were extracted 0.2 arcseconds away from the nucleus. And down here are example stellar kinematics. So again, the velocity and the velocity dispersion. So both of these galaxies are rotating, and they also show that signature of a peak in the velocity dispersion profile. So this galaxy reaches dispersions of 350 kilometers per second, And this is a low-mass galaxy, NGC 1022, and so it's reaching a smaller velocities version of only 60 kilometers per second. So we really, again, do have quite a diversity of galaxies here that we're studying. So the Gemini Large and Long program provides us with this unique and powerful opportunity to acquire a large homogeneous data set that will analyze in a consistent way. With this study and this investment of Gemini time, we will produce the largest homogeneous sample of black hole masses that have ever been carried out. So with this study, we hope to address the bias in the kinds of galaxies for which black hole masses have been measured. We're going to obtain, hopefully, a more complete census of the local black holes. We could reinvent the black hole scaling relations. And we just want to try to get a deeper understanding of the interplay between black holes and galaxies. So to conclude here, the past 2 decades have seen tremendous growth in terms of our knowledge of how black holes and galaxies are connected, but there's obviously still a lot that needs to be learned. The local black hole mass census is highly incomplete, and we still don't have a very good physical understanding of the essential mechanisms that are driving these empirical correlations. So what we need are more black hole mass measurements, especially at the extremes of the black hole mass scale and over a wider range of galaxy types. We also need to try to get a handle on the intrinsic scatter of the black hole relations. So from the EGT Massive Galaxy Survey, we've uncovered a sample of galaxies that are ideal for studying the upper end of the black hole scaling relations. We've studied 3 of these galaxies and so far have found very massive black holes with masses of 3 to 5 times 10 to the 9 solar masses. These objects are clear outliers from the ML relation, and given their similarities to the higher redshift red nuggets, could possibly suggest that black hole growth precedes that of the host galaxy. So ALMA provides this great opportunity to measure black hole masses through gas dynamical modeling methods. We're hoping to drive gas dynamical masses for 3 of the HET compact galaxies and then do a comparison to the stellar dynamical black hole mass measurements. Such cross-checks are desperately needed. And then finally, detailed investigations of large, carefully selected samples using this homogeneous approach is the ideal way to make major progress in the field prior to the next generation of extremely large telescopes coming online. So our Gemini Large program is off to a good start, and so hopefully we can have some interesting results to talk about based on these initial observations soon. So thanks. Uh-huh. Right. Well, so, I mean, yeah. So we want to, I mean, ideally what we want to do at that point is to be able to compare also to simulations where, so we're basically, once we have things like the slope and the intrinsic scatter and do these correlations apply to certain galaxies but not other galaxies, then we can go ahead and compare to predictions for what these relations should be based on things like simulations. So yeah, I mean, ultimately what we're after is trying to, as best we can, characterize these relationships, and then from there we can go ahead and compare to models to figure out what's going on here. No, I mean, I just don't think we have enough black holes in a wide range of galaxies. I mean, 90 black holes, yeah, I mean, that alone probably sounds okay, but when you break it down into different galaxy types, I mean, we're already starting to see hints that not all galaxies follow these correlations. So spiral galaxies, there's not a lot of black hole mass measurements. It's something we're trying to address with our large program. We're finding that they actually fall below the scaling relations, and they're showing something different. Well, you always find new physics when something isn't there, right? I mean, that's how you learn things. Right. 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 Yeah. So you're absolutely right. They're all over the place. people tend to think that the galaxies are overmassive relative to the local relations, just like what the HET compact galaxies are showing. But I don't even trust. It's really right. Right, exactly, yeah. But I mean, yeah. So I would, if you took a poll of people that study this thing, I think most people would say, yes, I think they're overmassive at, relative to today. But it's a belief. It's definitely, we do not know for sure. Well, actually, I think, and maybe someone who studies high redshift galaxies correct me if I'm wrong, but I actually think that higher redshift galaxies do show or we think they show rotation. So they show these like flat structures. We do think that they're rotating, and they actually haven't experienced the mergers to lose their angular momentum and build, your dispersion-supported elliptical galaxies today. So I think this is actually, the fact that we are seeing this like strong rotation is consistent with this idea that these galaxies are relics of the higher redshift galaxies. Oh, can the black hole grow by eating up the galaxy? Well, so I mean, it's not going to eat up the whole. So I mean, there's some accretion disk and material from the accretion disk is going to accrete onto the black hole, and it will grow through that means. Yes, I mean it's not going to eat up the whole galaxy, but no, that's very much an open question. Yeah. Yes. The growth of the black hole. Yeah, we don't know that at all. So I'm not even quite. Yeah, we don't know how to. We don't have a relationship like that at all. It really has not been looked at. Mm-hmm. The accretion disk? No. It's in the galaxy. Wait. Uh, no, I mean we are nowhere close to those kind of regimes, right? So I mean we're measure. So we cannot observe something like that. No. It's yeah. I mean we can't. Right. We absolutely cannot do something like that. GMT will not be able to do something like that. Right. Right. Yeah. Right. Right. From the shape of the lines. Yeah, I actually don't know. How bright is the disk? So, I mean, accretion disks have temperatures of like 1,000,000 degrees, so they're bright in the X-rays. I mean, none of the stuff that I've been showing have been any. I mean, we're not probing the accretion disk at all. We're not at those kind of energies. But yeah, I mean, over 1,000,000 degrees for an accretion disk. Actually, I think 3C273. I mean, if you go, I mean, there's AGNs that are closer, but quasar, like it might actually be 3C273. Yeah, just a little bit. um, so it's at a what's that? So what is it? Redshift of Like, I mean, I think. You know, I don't think it's crazy. I don't think it's crazy. Yeah. So, I mean, it's hard. Yeah, I mean, right. So you would absolutely have a problem with a quasar, but. Okay, so I did steal it from YouTube, but then I pasted two movies together. So I stole that beginning. I know. I stole the beginning part from YouTube, and then I pasted the Andrea Ghez UCLA group movie into it. You can find the beginning part. You can't find the end part. Well, you can find the end part, but separately. See me if you want the movie.
All right. Well.